Okay, so um, let's get started on NMR. Actually, before I start, any questions about IR at all? I think IR is fairly straightforward. Nothing crazy. Yes, go ahead.
Yesterday on the worksheet, the seventh one was like an ester. Do we need to know that?
No, so for you guys, um, you should be able to identify that there's a carbonyl peak and there's a C single bond O, but hopefully there'll be additional information that'll give away the ester as well. Does that make sense?
Yeah.
Yeah. But I mean, you should definitely see that 1710 carbonyl peak. And then again, you're scouring the fingerprint region for something in the 1,000 to 1,300 range to sort of consolidate that. But again, you will be given 3 different layers of information. And so once we finish the lesson today, starting tomorrow, I'm going to layer those things together and you'll really start appreciating them. And then there's one question that's really nice because it brings the retrosynthesis, or the synthesis pathway route sort of questions together with NMR and IR. So it's a really nice review tool for stuff that we've learned previously as well. So we're going to focus on the radio wave portion of the electromagnetic spectrum today. So nuclear magnetic spectroscopy, again, it's non-destructive to the sample. And you shine radio waves on the sample, and radio waves only impact the nuclei of the sample. So the idea is, people that are in physics probably know this already, but anything that spins create a its own magnetic field. So our Earth obviously has its own magnetic field. Electrons have their own magnetic fields. We talked about the fact that they spin in opposite directions so that they can pair up and overcome repulsive forces that are there. And then similarly, the nuclei of atoms spin as well. Okay, and that spin then generates its own teeny tiny little magnetic field. And so the idea is, when this magnetic field is spinning in one direction, if I want to flip that spin, so if it's spinning clockwise, in order for me to flip it into the counterclockwise direction, how much energy would be absorbed? And so depending on the nuclei and its environment, the amount of energy absorbed would differ. And so those would show up as peaks on your NMR spectrum. And we will use those peaks to identify the hydrogen environments. So we are focusing on proton NMR, meaning that we are going to focus on hydrogen nuclei. Okay, so the nucleus of a hydrogen atom. Now, nuclear magnetic spectroscopy, or NMR, is used with other atoms, but the catch is that they have to be odd numbered. And you won't have NMR for every single element on the periodic table. There's a few. So there's carbon-13 NMR. There's phosphorus NMR that I remember studying in university, and a couple of others, like handfuls. So our focal point is proton NMR. Okay, so the cool thing about studying proton NMR is that now I can think about the proton environments that are surrounding a carbon and its neighbor, let's say. Okay, and the very cool part about this is now I can now figure out exactly how many hydrogens I have per carbon, and I also know how the neighboring hydrogens are influencing these hydrogens, and I can figure out information about the carbon next to it. So a lot of cool implications. So up until now, you can deduce certain fragmentation patterns from the mass spec. You can figure out a molar mass, right? You can suspect certain non-metal presence within the mass spec, but you need more information. So when you add the infrared spectrum to this, now you can identify the types of functional groups that are present. right? And if I've given you the formula, then you can figure out the numbers of unsaturations, and hopefully the IR will confirm that in terms of the functional groups that are present. So is there an alkene? Is there an alkyne? Is there a carbonyl? But neither of those tell us the exact position of the hydrogens surrounding the carbons. Because once I can identify exactly where the hydrogens are positioned, then I can come up with a very precise structure. So NMR is a very, very strong analytical technique because it goes beyond mass spec and IR and really deduces the exact sequence in which the carbons are connected, and those connections are deduced based on how the hydrogens behave in the presence of radio waves. Okay, so the idea is you shine varying amounts of radio waves on the sample, and depending on the type of hydrogen environment, it will absorb a certain energy. So we talk about hydrogen environment. So if I like draw something like bromoethane, we know that the electronegativity of the bromine is present, which is going to cause this, right? We know about that already. But this also then changes the environment of these hydrogens. These hydrogens are directly connected to a carbon, which is directly connected to an electronegative atom. So their environment cannot be said to be the same. So these two hydrogens cannot be said to be the same, exactly the same as these three hydrogens, because there's this electronegative atom present. So what we do is we start identifying environments. And the environment has to do with, you know, where those hydrogens are situated and what's next to them. So clearly, these hydrogens have a different sort of um, impact, like in terms of the absorbance, as compared to these hydrogens. So what we can say, for example, is that the when the electronegative atom is there, it sort of pulls electron density towards itself, right? And so it kind of exposes the nuclei more, right? So think about the hydrogen; it's got a single electron that is participating in the covalent bond here. But if there's a sort of force that's pulling electron density towards itself, then it exposes the nuclei more. That's what we say. Now, these guys, the nuclei isn't as exposed as this, right? And so we can say that there's actually two different environments. And so these environments are based on what is happening around the carbon, sort of thing. Okay. And I'll go into more detail about that. So when we, absorb a certain amount of radio waves, we actually measure it in something called a chemical shift. So again, a chemical shift is designed so that you can use numbers, whole numbers, to deduce the presence of different environments of hydrogens. Okay, so we're saying these are more exposed, right? And these are less exposed because, or the nuclei are less exposed because they're not next to a more electronegative atom. And that's what I'm saying here. For example, the hydrogen of an alcohol will feel a different sort of, will be in a different environment as compared to, let's say, a carbonyl hydrogen. So, for example, an aldehyde. So this hydrogen and this hydrogen will have different um, um, chemical shifts because the type of atom next to them will, have different impacts on taking the electron density in. Or remember, we talked about alkyl groups having the ability to pump electron density back. So those factors affect the place in which the absorption happens. And so then we can now start generalizing, like generally when a hydrogen is hanging out next to an oxygen, it absorbs in this range. And when a hydrogen is, hanging around close to a carbonyl, it absorbs in this range. And when it's like a halide, it absorbs in this range. And when it's not next to a halide, when it's not sort of exposed or de-shielded, then it absorbs in this environment. So now on the spectrum, you have different places where these hydrogen protons absorb. So once again, proton NMR deals with the position of the protons. These protons are impacted by their environments. And by environments, we're referring to things that are nearby. They're atoms that are directly attached to the carbon, or even the atoms next door, so the carbon next over. Okay. So in order for us to be able to measure the chemical shift, we need a reference point. Okay. So in NMR, the point of reference is using tetramethylsilane, which is right here. So what they've done is they've used a molecule in which first of all, the carbons do not interact with each other, or they don't influence each other. Okay? Because they're not next to each other. And I will lay down rules for what constitutes impacting one another. Okay? So if you guys take a look at these hydrogens are pretty separated. Like if I have to try to influence the hydrogen on the carbon next to me, I got to travel 1, 2, 3, 4 bonds. 4 bonds is too far. So what we find is by using silicon and carbon, which are relatively, similar in electronegativities, let's say, the hydrogen environments are all the same. They all feel the same amount of shielding or de-shielding. So shielding is reserved for groups that are influenced very minimally by neighboring sort of electronegative atoms that pull electron density away. Okay, so these guys are not shielded, or they're very well shielded. Okay, things that are next to like highly electronegative atoms like nitrogen, oxygen, or a halogen are more de-shielded because you're taking electron density away and exposing the nuclei. Okay, so when you take these 12 hydrogens and you look at it, because I can't scroll up, because the environment is similar, there's only one peak that's generated. All the hydrogens are same. And so what they did was they said, fine, if all the hydrogens are the same, then we're going to assign it a value of 0. So just like, in UV Viz, if you're using a UV Viz, you'll use a blank to 0 it, or you tear your balance. This is basically zeroing your chemical shift. And so everything is measured relative to this very shielded hydrogen environment molecule. Okay? So the nice thing about this is you mix your sample with the TMS and you subject it to the radio waves. Okay? This sample is non-toxic and unreactive. So what you can do is you can kind of sort of separate your mixture and get back your original. So that's why it's still non-destructive. So the idea is these hydrogens are very well protected or shielded. They absorb upfield. Upfield means that they're not de-shielded. Okay. So due to its high volatility and low boiling point, it can be removed from the sample, thus regenerating the original sample. So TMS is very useful for us. So here is the scale that we will be looking at. The scale will go from basically 0 to 12, and it shows you the relative positions where you will find different hydrogen environments. So here's your TMS. This is your tetramethylsilane signal, which is your 0 mark. And then any hydrogen beyond that, any sort of organic compound, will now absorb above 0. Okay? And so the chemical shift will always be higher. The chemical shift is measured in parts per million. And again, it's an inverse wavelength quantity. And so we say that's measured in hertz. So shielding is happening when you are pumping electron density in, or when the proton is not surrounded by electron density withdrawing elements like elements. And we say that the absorbance is upfield, close to zero, because the tetramethane hydrogen proton environments are the most shielded. Okay, but when you have an electronegative atom next to a proton, and because it's exposed, it will absorb more downfield. So downfield is to the left, upfield is to the right. It's all relative based on the environment of the hydrogen. So here's a sort of general view of what is happening. So a typical hydrocarbon, hydrogen, is fairly shielded. There's nothing to impact its proton, and it's fairly upfield, right? Very close to TMS. Okay. If you start adding, different sort of environments, so hydrogens in next to oxygen with water, hydrogens in benzene, hydrogens in aldehydes, and so on and so forth, then you'll notice that it starts going more upfield. And so this now serves as a really nice tool for us to sort of indicate not only the functional groups that we suspect are present in the IR, but now we confirm it again as to where the proton that's next to that functional group is absorbing. Okay, so the information that we can get from an NMR spectrum. So an NMR spectrum, we're going to be looking at high resolution NMR spectrum. And in a regular NMR spectrum, first of all, you can figure out the number of environments, the number of different types of hydrogens that are there. So for example, I said that bromoethane has two environments of hydrogen. So the proton environments are two, okay? So I can call these protons A because they're next to that bromine, and then I can call these environment B, or I can say that they're in a different environment as compared to these two protons. So right away, the number of signals tells you the sort of proton environment. So for my bromoethane, I will expect two peaks, okay? And the two peaks will depend on the position. So let's think about this. This one will be more upfield, right? Because it's more shielded. The protons are more shielded. This one will be more downfield, right? Because it will absorb downfield because there's a bromine next to it that is withdrawing electron density, and therefore it's more deshielded. The protons are. The protons nuclei, right? We're looking at the proton nuclei. So right away, even though you guys don't know what's happening here with the madness, we can say that there's 1, 2, 3 environments in my ethanol. Okay, so let's draw ethanol, right? Ethanol is simple. So if I look at the proton environments, I agree. There should be 3 environments, right? First of all, the oxygen that's directly linked to the, the proton that's directly linked to the oxygen obviously feels a stronger deshielding effect, right? Now, these hydrogens here are also feeling some effect, but not as strongly as this one. So we can't say that the environment is the same. So this is a different environment. And the carbon that's furthest away from this, the shenanigans with the oxygen being present, this feels the least deshielded, right? Because the oxygen is so far away. So I can say that I have 3 environments. There they are, 1, 2, 3. Okay. Now, the position of the signals we've already talked about. The positions of the signals depend on what is the environment of the protons. Clearly, the hydrogen that's next to the oxygen is absorbing more upfield, right? And the methylene, the CH2 hydrogen protons, are further upfield from the methyl ones because they're more deshielded because of the oxygen. So the position of the signals tell us what is next to my um, protons. So it gives us information about the hydrogen environment. The signal intensity is basically they take the area under all these little peaks and they add it up. And so sometimes on a mass spec, there's an integration trace that's given. This is integrated. So notice how it's giving you a 1 to 2 to 3 ratio of hydrogen environments. Okay? Now, will it always give you the exact number? No. So for example, if I have 3 hydrogens to 9 hydrogens in 2 environments, it may give you a 1 to 3 trace. Okay? And so you may have to like take the multiple of that value to figure out what your actual hydrogen numbers are. So sometimes it works out if it's a simple molecule. More complex molecules, you have a ratio, the simplest ratio, and then you're going to determine how you need to manipulate that ratio given some sort of, chemical, um, like a condensed formula. So not every single NMR will give you this trace with the numbers. So sometimes they'll give you the trace, but they won't give you any numbers. So you literally have to sit there and take your ruler and go, okay, this is 1 centimeter, this is 2 centimeters, this is 3 centimeters from like sort of the most vertical region, top and bottom. And then you're going to base your ratio on that. Okay. So this is a really nice, generous proton NMR because it's also giving you those values. The last one is where most people get very nervous. So the splitting of the signal. The splitting of the signal. So when you are 3 bond lengths away, 3 bond lengths, you can split or impact the nuclei of a neighboring proton. So for example, when I look at my bromoethane again, these hydrogens will not be able to influence each other's fields, magnetic fields, but they will influence the neighbors. So notice how I'm 1, 2, 3 bond lengths away. Anytime you're 3 bond lengths away, splitting can happen. If you're more than 3 bonds away, splitting will not happen. So for example, this hydrogen here could 1, 2, 3 impact these protons, but 1, 2, 3, 4, but these protons will not be impacted and there won't be any splitting. So if I go back to tetramethylsilane and I use this rule, notice how this is 1, 2, 3, 4 bonds away. That's why the proton environments don't impact each other. That's why there's only one peak. Okay, so 4 or more, no splitting. So what happens is the neighboring protons have the ability to influence the arrangement of the nuclei. Okay, so splitting works like this. I'm going to introduce it and then we're going to come back to it. We're all going to take a deep breath. We're going to do more and more and more until everyone's on board. And every single person, if I have to today, I don't care about your morning face. I want to see you guys work on this. It's absolutely essential that everybody works today. Write something down. Do not wait for my answer. Okay? So let's take a look at um, bromoethane again. We identified that there are 2 environments, right? Environment A, right? And environment B. Hydrogens that are in the same environments do not influence the hydrogens don't influence each other's nuclei spins, okay? But they do influence the neighboring different environment protons, so long as they are 3 bonds away. If they're more than 3 bonds away, then no. So this is what we expect in low resolution NMR. We are going to get 2 peaks, 1, 2, right? So we're going to get 2 peaks. This one will be downfield, easy peasy. Everybody should have that under control. This will be upfield. How will this split? The rule is, for example, for these protons here, these 3 protons will influence these 2. Okay? Understand that these 2 are considered to be 1 peak, but this peak gets split by the influence of these 3 neighboring protons. So it's always itself plus the number of hydrogens splitting it. So this peak will split into 4. Itself plus the 3. Got it? So you're going to start getting used to splitting patterns and go, oh, I know, this is an ethyl methyl. This is an isopropyl. This is a tert-butyl. Like quick, you'll start noticing these things. Now, this peak here is getting influenced by environment A, right? So these hydrogens are all equivalent. They're in the same environment. They themselves don't split each other, but they get split by the neighboring proton. So this signal here will get split by these 2. So it's itself plus 2, which means this will split into 3. What does it look like? Usually, this is how it rolls. The signal is sort of evenly spread. And I don't care how you draw this, but I'm showing you. So it's always, for 3, it's short, and then tall, and then it's short. This is called a triplet. Okay? The 4 splits like this. 1, 2, 3, 4. And this is called a quartet. So the rule is anytime I see a triplet quartet, I can close my eyes and go, I got me a ethyl-methyl combo. And it's the one that's split into the quartet. If it's absorbing downfield, it's got something hooked up on it. What is it? Well, I'm going to go to my mass spec and look for the isotopic distribution of bromine, which is 50 to 50%, right? Isotope 79 and 81 are almost like 49 to 50% distribution. So I'm going to use that knowledge to confirm what I suspect. Okay? Guys, any questions so far? Everyone's with me? I love it. I love it. Okay. So deep breaths. I have this under control, okay? The way I teach it, you're going to love NMR. So now that everyone is actually following along or just too shy to say anything, we'll go into a bit more detail about ethanol. So low resolution NMR has no splitting. Low resolution NMR then doesn't give us the exact number of hydrogens and where they're located, right? You can suspect it, but the splitting confirms like this is the way this is distributed, okay? So we in HL do high resolution NMR. And the NMR that we're looking at is proton NMR, the splitting of proton nuclei. We looked at ethanol's NMR earlier to identify the environments. Now we're going to talk about a couple of things here. Remember how I generated that pattern up top where I'm like triplet looks like this and doublet looks like this or quartet looks like this? Why did I choose that pattern, right? Why not make all the peaks exactly the same? So I'm going to show you why. Now, the other additional sort of issue that we have with the choice of molecule that I selected, which complicates the spectrum a little bit more, is that usually in IB, what they say, or they tend to, I don't know, they may change their mind, is that like hydrogens next to like say an oxygen will not necessarily do any splitting. So if we did this simple style, we would expect a similar pattern as bromo ethane, I would expect a triplet quartet here. The more complicated part is that in the spectrum that I have, the hydrogen also splits. The hydrogen on the oxygen also splits it. So what I'm trying to say is something like an aldehydic hydrogen, we assume it doesn't impact the environment. Now, depending on where they get the spectrum, if you have sort of a confirmation of what you think you're supposed to get, and then it's a bit more complicated, understand that other hydrogens that we're trying to ignore are playing a part. So if I take a look at environments for my ethanol, here's environment number 1. Everyone will agree, right? It's further away. And it's not attached to anything different. This one is feeling the effects of this oxygen, so environment 2. And then, of course, my alcoholic hydrogen here, environment 3. So let's pretend that this hydrogen is not there and doesn't influence this. I want to show you why the signal is how you see it, right? So we are expecting, if we ignore, so I'll write it down so you remember that I ignored it, ignoring OH proton effects, okay? What I'm anticipating is for this one, I'm expecting 1 peak, which is getting split by this. So I'm expecting a triplet here. And over here, I have 1 peak for these environment that are getting influenced by 3, right? So I'm expecting a quartet, right? If I keep it simple, like bromoethane. I want you to understand how these peaks are determined. So we know that the nuclei of these different environment hydrogens influence neighboring proton nuclei. But when we look a bit closer, so they're calling, it says we observe a triplet when we look at the methyl peak, right? So we said over here, this is a triplet. So the question is why? Well, we're going to look at the neighbors. Okay, these are the neighbors. How are the neighbors influencing the methylene peak? So what they're saying is the neighboring proton, when the field is applied, can either both go against the field, okay, both of those neighboring hydrogens can go align against the field, or they can align with the field, or one can go against and the other one can align, or the other one can go against and the other one can align. So think about the probability. So in terms of probability, it's a 1 to 2 to 1 ratio, right? Hence, I draw my triplet that looks like this. Okay, horrible triplet. I'm going to do it again. I do nice triplets. If there's something I draw good, I draw nice triplets. A little better, still sort of horrible, but you guys get the idea. So the triplet is based on the height, which is based on probability of arrangement. So 1 to 2 to 1. Okay, so if we look at the quartet, so now we're looking at the methylene. We're looking at the methylene hydrogens. Well, they're getting influenced by 3 methyl proton environments. Okay, so the 3 can either go against or line up, and then you've got all these different probabilities. So I get a 1 to 3 to 3 to 1 ratio in terms of probability of these nuclei aligning. So the splitting is actually how the neighboring protons are influenced or influencing the hydrogen protons. So when I draw a quartet, I go 1 and then double the height, or 3 times the height, and then that. Now, am I ever going to be marking you wrong on how you draw the splitting height? No. Okay, this will become more important, like say in university. But at this point, if you can tell me, Miss, this is going to be a triplet, this is going to be a quartet, and you draw me 3 peaks and 4 peaks, I am as happy as can be. Okay, I'm giving you reasoning as to where that splitting pattern and height is coming from. okay? So do I expect you to sit there and give me all the possible arrangements each time you do a question? No. Do I expect you to know the splitting pattern? Yes. Okay, triplet, quartet, done. The heights of them, when you see them, you'll get used to seeing them in that particular way, and it's good. It'll, you know, sort of get you comfortable with what you're looking at. So the rules for spin-spin splitting. The rule is always itself. The number of peaks of a signal is given by the n plus 1 rule. I always go, so this is how we did it earlier, right? For CH2 and CH3s on the BR, what did I say? I said itself, right? And then it gets split by neighbors, which is 2. So it's going to get split into 3, right? Itself, and it's going to get split by 3 other ones. So then you get 4 lines, right? So you get your quartet and triplet. Okay, so that's where this n plus 1 rule comes from. Okay, it's always itself plus the neighbors that are doing the splitting. Okay, other rules, equivalent nuclei do not interact with each other. So this is why we kept these hydrogens together. Because remember, that would be nuts. If this hydrogen started splitting this one and this split one, and then these guys split each other, that'd be nuts. So they don't. Hydrogen environments that are similar do not influence each other. Okay? Splitting cannot happen when you're more than 3 bond lengths away, and this is pivotal. So you don't have to worry about splitting patterns. Okay? So let's go back to ethanol. Let's go look at this ugly that we have here. So without considering the impacts of the protons, right? If we ignore it, we are anticipating a triplet quartet, right? And then we're going to say this is a singlet. Nothing will happen to it by itself. It doesn't do anything, okay? But if include OH effect, then what are we going to get? So let's figure that out. Let's figure this out. What's happening here? It's a lot of splitting, but no problem. We've got this under control. So let's redraw our ethanol. And we're going to look at the environment. So 1, there's the second one, and there's the third one. Okay, so let's see what is going to split what. So these hydrogens are 1, 2, 3 bonds away. So these protons can definitely split these hydrogens, but can this one? So let's count 1, 2, 3, 4. So this alcoholic proton will not be able to split the methyl. So this methyl, itself, is going to get split by these protons. So we're going to expect a triplet here, right? No problem. For these protons, I've got 1, 2, 3. It's going to definitely get split by these protons. But watch, 1, 2, 3. It's going to get split by this as well. So these guys are going to get split by 1, 2, 3, 4. So itself plus 4 gives me a quintet. 1, 2, 3, 4, 5. A quintet. Take a look. Take a look. Okay? And then this proton will get split by these because it's 1, 2, 3 away. There's 2 hydrogens that will split this, right? And so we're expecting a triplet. And you'll notice that it's very sort of squished together. And this is the problem with the splitting of things next to highly electronegative atoms. So you're expecting a tripling pattern, but you don't really see it. Okay? So this, depending on what you're looking at, may look more complicated than necessary. If it does, it's because there's some influence happening with the proton that we sort of consider as non-active in grade 12. All right, deep breaths, deep breaths. Here is the chart from your IB data booklet. I wish I'd done that for your IR one, so I'll get that. And so these are the absorbance or chemical shifts, I should say, for different types of protons. So we know our TMS is 0. It says it right here, up here. Where's my, right? Just a regular, plain Jane proton. Regular, happy, happy next to another, let's say, carbon with hydrogens, will absorb in the 0.9 to 1 range. So very close to 1 because it's nice and shielded. Okay. Sorry, so this one is just a hydrogen off of, let's say, a methyl. This is now down, proton down chain sort of thing in the middle, 1.3 to 1.4. This is if it's like a tertiary sort of thing going on. It will absorb around 1.5, okay? The protons next to like a carbonyl, they're showing an ester, but the carbonyl hydrogens will go upfield, okay? And there's a range. So if I take this off and I put a carbon here instead of the ester, then it goes further up. Okay. If I'm looking at the hydrogens off of my benzene ring, around the 2.5 to 3.5 range. Okay. For a triple bond, it's here, a halogen 3.5 to 4.4. Oxygen next to like almost like an ether sort of thing. Those hydrogens will be around 3, 3.4, and so on. Okay. The carboxylic acid is usually off the charts, like quite literally off the charts, because it absorbs really, really high. Same thing with the aldehydic one. Where's the aldehyde? It's missing. Aldehydes are very high too. And so they're off the chart sort of things. The other one that's missing here is benzene. Benzene, there's something very cool about benzene. It likes the number 7. So remember, for mass spec, we're looking at a peak around 77. For this one, we're looking at a chemical shift at about 7 parts per million. Those are the protons on a benzene ring. These guys. Okay, so if you see something around 7.2, suspect that you're looking at protons on a benzene. Okay, so aldehydes, I want to say is like 11. These are, and carboxylic protons are especially deshielded, and they're found further down the line. So we're going to take baby steps. Baby steps. I'm not going to jump right into looking at NMR spectrums. The idea is we're going to first draw anticipated NMR spectrums. And then we're going to confirm. Because if you can draw them, after a while, when you look at them, you'll see patterns. And it will become much easier. So, guys, I want you to draw the complete structure for 1,1,2-tribromoethane. I want you to identify the number of hydrogen environments. I want you to identify the position of the signal, and then I want you to split it. Okay? So we're all going to work together on this one first, and then slowly I'm going to stop holding your hand, and you're going to go solo. Okay? So let's draw this. Okay? Now, how many environments, you guys? How many environments?
Two.
Awesome, 2. So it's pretty obvious, right? So we can say that these 2 hydrogen proton environments are feeling a very different impact because of the single bromine as opposed to this lonely only here. So we're going to call this, let's call this proton A. We'll call this protons B. All right. Now let's go back to the chart and figure out where we're expecting absorption. The chemical shift for a halide is around 3.5 to 4.4. Okay. Our range is, so the ppm for a halogen is 3.5 to 4.4. Now, guys, which one will hydrogen A, you're just going to put up your hand. How many people think hydrogen A will be 3.5? Hands up. Hands up. Okay. Anybody else want to try? More hands are going up. Good. Okay. So the rest of you either are confused or think it's the other one, which is fine. So let's take a look. So when we look at this hydrogen environment, it's next to two electronegative atoms, aren't they? So this is going to have a lot of its electron density sort of pumped away. So this is more deshielded, right? And this is less deshielded because it only has one bromine next to it. I would say that this one would absorb around 3.5 and this one probably around 4.4. Or definitely I would say it's higher. Agree? So this will be more upfield. This will be more downfield. All right, let's organize the signals. So if I'm over here, and this is my TMS, right, at 0, then proton B will come first, proton A will come down the line, okay? But before we put the signals in, what about the splitting? So we know that something's gonna, so here's 1, 2, 3, 4, 5. So we're anticipating a signal around here, and we're anticipating a signal around here, right? We're anticipating peaks here. Luckily, we're not doing low resolution NMR, we're doing high resolution NMR. So let's think about splitting. These two can be influenced by this proton nuclei, correct? If it's 3 bond lengths away, let's count. 1, 2, 3. So this signal here will start by itself, right? And it's going to get split into 2. So I'm going to end up getting 2 peaks. So this is called a doublet. This proton here will get influenced, so it's itself getting split by 2 others. So there's going to be 3 total. So I'm going to get a triplet, right? So when I draw this on my NMR spec, I'm going to have, for this one here, it's going to be a doublet, okay? And then over here, it's going to be a triplet, okay? Any questions? Any questions? So this is for A, and this is for environment B. The silence makes me either want to celebrate or want to cry because I don't know what you guys are thinking at the other end. All right, take a look at ethylbenzene, okay? Take a look at ethylbenzene. Identify the environments, you guys. Remember, don't forget that the benzene has protons. I already told you it likes the number 7. I want you to draw it, label the proton environments, figure out where they absorb, and then I want you to split. All right, everybody on board that we have three environments, right? Three environments. Why three environments? Because these hydrogens here are feeling the effects of this huge pi cloud here, right? And the hydrogens that are further away aren't feeling that same sort of pi cloud influence because they're further away. So we have to have three environments. So we'll call it environment A, B. The hydrogens on the benzene, that's up for discussion. At our level, we're going to say they're equivalent. I mean, these two hydrogens here are closer to this alkyl group and may feel some sort of electron donating effects. And so in higher level organic, they'll say these two are different from these three. For us, okay, we're just going to leave it. We got enough problems to deal with right now, just trying to figure out the fundamentals. So we're going to say that this is group 3, or C. Where are the absorbance? So this will be closer to like 0.9, right? This will be a little bit further up, around 1, right? And then these will be around 7. Everyone should be okay with that. It's just looking at the chart. Now, splitting. So let's look at the first one. The methyl hydrogens will get split by the carbons next to it, but they're not enough. So say I put a hydrogen here and I count 1, 2, 3. These protons are close enough, but 1, 2, 3, 4, 5. The benzene ones can't interact, so there's no splitting, and so therefore it's itself getting split by 2 neighboring hydrogens. So it is going to be a triplet, right? And then for, let me draw it a bit more neatly. I'm not drawing the best triplets today. I don't know why. Okay, so we're expecting a triplet, and we're expecting one node to shut down at least once a period. So we're getting a triplet here. And then for B, now B is next to the methyl. It's 4 carbons, or 3 carbons, I'll get my wording right. It's 3 bondlets away. So the neighboring protons will influence or split this signal, right? It's going to split it by how much? Well, it's itself plus 3 hydrogens splitting it. So it's going to be a total of 4. So I'm going to get my quartet. Now this looks similar, doesn't it? We talked about triplet quartet. So in your mind now, an ethyl will always be triplet quartet, right? So you're going to start looking for certain features. Be like, yeah, I see that. There has to be an ethyl somewhere attached on this molecule, right? The protons on the benzene, well, let's see if these hydrogens can impact it. So 1, 2, 3, 4. No. So these hydrogens are not able to split the protons within the benzene ring. So we're expecting a singlet here, right? Sometimes you'll see the signal split into like a lot, and that's because they're doing stuff with each other within themselves, and we're going to ignore that. So in terms of plotting this, TMS, right? Let's go up and make sure. So a regular end methyl proton will be 0.1 to 0.1, 0.9 to 0.1, and then mid chain is 1.3 to 1.4. So let's do 1, 2, 3, 4, 5, 6, 7, right? Oh my God, destroying the, I have to write at an awkward angle, just the way things are positioned over here at home, and sometimes it just doesn't work. So 1 and 2. So really, we're anticipating a triplet around this area, right? And then we're anticipating a quartet around this area here. 1, 2, 3, 4. And then I'm anticipating a singlet right here. And I'm drawing the peak height a little bit higher because the area under the peak will give you a ratio, right? So this will be a 7 to 2 to 3 ratio. Any questions, you guys? Yes.
So for the ethyl beside the benzene,
Yeah.
I wrote that it would be like the 2.5 to 3.5 because on the chart it says if you have like a methyl beside a benzene, that's what it'd
Let
be.
me shade. Did I miss something? Oh yeah, that's okay. Yeah, that's better actually. I missed that. You're right. Let's shift it downwards. So really, yeah, good call. Good. Yeah, we're gonna put it right here. Sorry, everybody. Sorry. So we'll put it around 2.5. 1. Yeah, I should have looked at that too. I didn't. Yeah. All right, everybody, let's roll on to the next question. So if you feel like you want to know what the actual NMR looks like, guess what, Miss Alma did? So here's your doublet, triplet that we deemed for the first question. Here's the one that we just did. Okay. They're making the no, this is 3-methyl-2-butanol. That's later. I lie. So here it is. This is what we just did. Here's your methyl proton very close, right, to 0. Here's the one next to the benzene, and here's your aromatic benzene. So notice how it's whack. Don't worry about it. And it's above 7. Yeah, sometimes like 7.2, 7.3 because of the influence of the substituent. So anything around 7, suspect aromatic. All right, let's go back. So start working on 3-methyl-2-butanol. We'll see how far we get. For homework, you're going to do isopropyl propanoate. You're going to draw the NMR. You will not cheat and look at the NMR because then you won't learn. But once you're done, you're going to look at the NMR and see how you did, and you'll probably do good, and you're going to pat yourself on the back. And if you don't get all of it, no problem. We do it all over again tomorrow. Okay? If I have to reteach this lesson all over again tomorrow, I'll do it all over again. I don't think I'll have to. Because if you listen to it today, you should be good. But what I want to do now is just build. You guys are going to become lean, mean NMR machines by the end. So you draw and work on that. I'm going to do attendance, and then we'll see where we end up today. Mohit.
Here.
Amisha. No Amisha. Must be a test around the corner.
Her Wi-Fi wasn't working.
Oh, okay. Thank you. So you were here. I hear there's a math test, so I'm anticipating people not being here today. Abby?
Here.
Victorville?
Here.
Karm?
Here.
Manthan?
Here.
Jasraj?
Here.
Siraj? No Siraj? Navdeep?
Here.
Ankita?
Here.
Sana?
Here.
Geetika?
Here.
Harsh?
Here.
Gurjot? Gurjot? Aisha?
Here.
Shavang?
Here.
Ananya?
Here.
Vidhi?
Here.
Abhi?
Here.
Mari?
Here.
Visha?
Here.
Viraj?
Here.
Johnny?
Here.
Birchan?
Here.
Berman?
Here.
Kelp?
Here.
Niyati?
Here.
Raj,
Here.
Nimmer,
Here.
Prasanna,
Here.
Akash, Lisa, Sean.
Here.
Okay, thank you, you guys. All right, let's see what we can do with the structure. Maybe what we'll do is we'll identify environments and then you guys can come up with splitting patterns on your own. The more you do on your own, the better. Go through the pain, get it wrong, it's okay. Getting it wrong means there's processing happening. And I promise you'll come back and you'll do great. All right. So let's take a look at this. So these methyls here are next to a carbonyl, right? And the hydrogens on these are different from the hydrogen that's next to the carbon that's directly attached to the hydrogen here. And the reason why this is different is because it's attached to two methyl groups which have electron donating abilities. And so its environment is different. So this is one. And this hydrogen by itself is two. And then these two, though, are pretty much the same in terms of what they're next to and what they're feeling. So we're going to bunch up these 6 hydrogens together. So we've got 3 environments pink, green, and yellow. Let's start talking signals. So this time I will look at the numbers instead of leading you astray. So we're looking for proton environments near a carbonyl. So proton environments near a carbonyl are in the 2.2 to 2.7 range, right? So in terms of the protons that are feeling the effects of the carbonyl the most, it's these hydrogens and this hydrogen. But this hydrogen gets shielded by the protons within the alkyl groups here. So it doesn't feel the impacts as much as these do. So I would say these would be more in the 2.5 range. Okay. This would be, oh my God, the second proton, so this would be 2.5-ish. This would probably be, I'd say like 2.3, and then I guess this would be 2.2. Or higher, even lower. 1, 2, 3. Yeah, ish. Okay. So in terms of splitting, let's see who can split who. 1, 2, 3. This hydrogen can definitely impact these hydrogens and vice versa. 1, 2, 3, 4. So these guys are lonely. So you're going to get a singlet here, right? Too far away. 4 bonds away means no influence of neighboring nuclei. Over here, this hydrogen will get split by 1, 2, 3, 4, 5, 6 hydrogens. So it's itself plus 6, which means this is going to be a septet. Okay? And then these hydrogens here will only feel the splitting of this neighboring one, so this will be a doublet. Okay? So we're expecting sort of this pattern. So we're expecting the singlet to be the most downfield, right? Followed by the septet. So 1, 2, 3, 4, 5, 6, 7-ish. And then further down the line, the doublet. Okay, so let's scroll and see how we did. Which one is it? It's the 3-methylbutanone. And that's what we got. There's the doublet, right? There's the singlet. There's the septet. Okay. It may be hard to, sometimes the peaks, like so over here, I got 1, 2, 3, 4, 5. It's hard to see these tiny bumps here because they're so small. So don't get alarmed if the numbers don't measure up, especially in a multiplet, right? Multiple peaks are sometimes hard to sort of consolidate. So homework, work on this, see how you feel. And tomorrow I flip it. I flip it on you and we look at pictures and we solve some puzzles, okay? So we're going to call them puzzles, and everybody loves solving puzzles. Guys, we're officially done. We're officially done content. Yay! Aren't you guys happy? You should be so happy. Now you can, just continue practicing. You have now a good week and a half of studying, right? So you guys should do really, really well on the test. I'm sure you have your IB stuff that you have to